Well, one of the more important things that we have to talk about before we get too far into acid-base chemistry is this concept of concentration. And we have to talk about how we calculate concentration, how we describe it, and so on. At the end of the video, we will come back and make sure that you've picked up all of those important objectives. All right? So the first thing we should probably talk about is molarity. And generally, molarity has a capital letter M, and what that stands for is moles of solute, the stuff we dissolve, moles of solute divided by liters of solvent, the stuff that we are dissolving. Now, this is not just for acid-base chem, but this is very useful for what we're going to talk about here. And we could take this a little bit further and call it moles. And there we go, moles per liter. That's one of the more common things. Later on, you will find out that we use brackets. Brackets mean molarity or moles per liter. So just get used to these ideas that molarity is the most common way of describing concentration in chemistry. So I think it's probably easier if we just do a simple calculation and get started. So let's say that we take 2.00 grams of sodium hydroxide and we dissolve to 1.50 liters. All right, well, let's make sure we get that right from the start. What does that really mean? Generally, when you dissolve or make a solution in chemistry, if you're really trying to get it exact, okay, you have this mark here on this volumetric flask. That's what this is called, a volumetric flask. And it's very exact, and it's very expensive, by the way, but it's exactly 1.500 at 20 degrees and so on. And so what you would do is first take the 2 grams and dissolve it in maybe a 500 ml sample of water. Okay, so there's your little pellets of sodium hydroxide. Excuse me. And you would add water and dissolve it first. Okay, because trying to dissolve it in here is really hard to do. So you do it in here first, and then you would put it in here, right? And then you would add more water exactly up to this mark. Now what that means is you don't have exactly 1.500 liters of water, right? Because some of that, not much, but some of that is this dissolved pellets. Okay, so you're just under 1,500 mLs of water. But that's how we do it, okay? And sometimes it's a big deal, other times it's not a big deal. Anyway, that's how you do the dissolving here, is you dissolve it first and then you water it down. So how do you calculate the concentration here? Well, we take the 2 grams of sodium hydroxide, and you have to first convert it to moles. And so 1 mole of sodium hydroxide, right? This is why we had to learn formula mass earlier in the year. This, if you add up sodium plus oxygen plus the hydrogen, you get 40 grams. We're not going to do that now, but if you take this, it's 22.98 on the periodic table, plus 16 plus 1. Okay, so do that step first. 2 over 4 is 0.5. 2 over 40 is 0.05. And we should keep 3 significant figures. Watch. That way we know. Right? Because you have 1, 2, 3. 1, 2, 3. So you're going to have 1, 2, 3. That's why you have 3 significant figures. Okay. The second step is take 0.0500 moles, and you really need to write this out. And then you put 1.50 liters. Still have 3 significant figures. Okay. Now, 5 out of 15, right, would be 0.333. But why don't we save you time? And we'll just do 0.05 divided by 1.5. There you go, 0.003. Okay, so 0.0333 moles per liter, or 0.0333 molar, right? That's how you would do it. You should probably also get comfortable with this. All of those are perfect examples of what you do, right? So that's how you calculate molarity. Another example, though, is what if we wanted to find out how many grams of a substance we have in a sample, right? Let's take this beaker of stuff here, and we are going to say that it is 0.873 molar calcium chloride, right? It doesn't have to be an acid or a base, but 0.873 mole. What that means is you have 0.873 moles of calcium chloride per liter, okay? But what if we don't have a whole liter, right? Because making a liter of this stuff might be expensive. It might be a lot of chemical that we don't need. Sometimes we don't need a whole liter, okay? So what if we had a 400 ml sample, right? What if we wanted to take out a small bit and we only needed 21.6 mLs? Okay, then what? How much are we actually getting of this calcium chloride? Okay, so this is another classic example of calculations that you will do. We can do both of these, and they're good examples. Okay, so let's start with 400 ml. So what if we didn't make a whole liter? That's what this means. This is 1 liter here. But what if we didn't make a whole liter? We don't want to use all of that stuff. How many grams of CaCl2 needed to make 0.873 molar, to make 400 mLs rather, of 0.873 calcium chloride? Okay, not the best grammar. I'm not worried about that. So what do we do? All right, so we're going to take this, and generally my rule about chemistry problems or physics problems is you start with what you know, start with what you have. So you have 0.873, 0.873 moles of calcium chloride. This is why you need units, so you remember how to do the problem. And this is per liter. Let's first convert this to moles, and then we're going to go to grams. This 400 is actually 0.400 liters. Okay? So 0.873 gives a 3492. Generally, the rule is keep significant figures until you're done. Okay, you could round it. AP Chem does it that way, but this is fine if we just keep that there. Okay, 3492 moles of calcium chloride. The next step isn't that hard. Now we take 0.3492. That's the moles of calcium chloride. This is why you keep units, because you have to know what you're doing here. We're going to multiply 1 mole of calcium chloride. And if I add that up, that's 40 plus 2 of these, 35.45. So that's 70.9. So this ends up being 110.9 grams of calcium chloride. This is why you leave your number in your calculator. Okay, don't delete every time you do something. Times 110.9. Okay, 3872. Right? 3872. However, we can't keep that. You see this? Right here. This is 3 sig figs. He's the fewest, so we have to go back. We can't keep all 4. So all we can do is 38 7 grams of calcium chloride. Okay? You should learn how to do this. If you take out a sample from a solution, you should know how many grams are in there. So the whole thing, we could do that too. We can figure out how many grams total are in here in 1 liter. But we only need 400 mLs. I'll leave that to you if you want to do that later. Okay? Let's take another look at the example here. What if we only took out 21.6, right? So your instructor makes a batch of this stuff, and they said you only need 21.6 to carry out the chemical reaction. How many grams are you getting? Watch again. You start with what you have, 873 moles calcium chloride. That's per liter. Okay, I'll let you catch up. Watch this. You're canceling out the liters. That's really what you're doing. 21.6 mLs is 0.0216 liters. Right? So this is like 2.1% of this. It's going to be small. All right? Let's do that. Clear? So it's 0.873 times 0.0216. You get this number. 0.0188. 0.0188. And we could call it that. If we round it, okay? Don't forget, this is moles of calcium chloride. You should instantly be able to convert this to 1.886 times 10 to the negative 2, because that is going to be very important later on. Being able to convert to scientific notation just like that. All right, so now what? Once we have that, 1.888, leave your number in the calculator. Don't delete. Right, 1 mole of this calcium chloride we talked about before weighs 110.9 grams. Really, you do have to write out all of this. It gets kind of annoying, but that's how we do it. So what do you have now? Leave that in there. Times 110.9. Okay. So you're getting 2 grams out of that stuff. That's pretty strong. 2.09 grams of calcium chloride. So now you know how to find out how many grams are in a sample. Okay? So those are the 2 main ideas of how to deal with those calculations. All right? But there's another concept called the dilution formula. And this is very well known, and you really need to learn this, the dilution formula. And it has a couple versions. When you find out what it actually means, it seems almost silly. Okay? The most common one is M1V1 equals M2V2. And that means M is molarity, right? But watch this. Molarity, M over L, moles over liters, times liters, right? And then you have the same thing over here. It turns out it's moles of 1 equals moles of 2. You're just finding moles equals moles. That's really all you're doing in the dilution formula. You're just finding out moles. Okay? But another version is if you have solution A and solution B, right? For example, acid and base, right? You could do concentrated and dilute. That's why we use subscripts all the time, so that we can label things. So any of these work, and we'll talk about why these are useful for what we're doing, especially this one as we get into pH. A less common version is when we use C1V1 equals C2V2. This is older, but some people prefer it, and that just means concentration times the volume. Concentration times the volume, right? But it's still going to be the same. The concentration here is still moles per liter. Okay, so we should be good there. All right. So, okay, so why does this even matter? Why do we have to know this kind of stuff? All right. you can only make dilute solutions from concentrated. You can't go the other way around. All right? So here's Benway's lab. And I make concentrated stuff for people to work with, okay? Or sometimes I get really strong stuff and I have to dilute it before I take it to class, okay? So here's a situation where I make a 2.00 molar HCl. That's not the most dangerous stuff in the world, but we don't need to be walking around with it, all right? So here's our hydrochloric acid, all right? But I tell you that you don't need this strong. You need to have a smaller sample. So I'm going to say you're doing a lab and you need 50.0 mLs, and you need to you have to have it dilute at 0. Let's pick this molarity of HCl. Okay, so that's what Benway tells you. You got to make it. You're going to take a small sample of this. We'll talk about how much, but you want to dilute it. So it's diluted more than half, right? It's diluted more than half. So here's how you set it up. The molarity of the concentrated times the volume of the concentrated should equal the molarity of the diluted times its volume, right? You're trying to find out how much of this do I need, right? How much of that stronger stuff do I need to dissolve? So this is why you learned how to rearrange equations. The volume of the concentrated stuff, keep MdVd over here, and you're going to divide by MC. Now this is what I want you to do. Get in the habit of doing this. I really want this equation to look like this. That's what it really should look like. In college, that's how you do it, okay? It tells the professor that you know these volumes are the same except for this ratio. The dilute concentration over this. Now think about that. Before we even get into the math, the dilute is going to be 0.75, and then the concentrated is 2, right? And you know that this fraction is less than 1. It's fraction, right? It's less than 0.5, right? It's actually less than 0.5. So it turns out it's going to be about 37%, I believe. Okay? You don't have to do that, but I'm just showing you that this ratio is less than 1. So when you multiply this volume, you're going to get a smaller number here. What do I mean? Okay. What was the concentration of the dilute? You need 0.75 molar. Concentrated stuff. This was your 2 molar. Okay? How much do you need? Diluted. You need, and you could leave it as 50 mLs. That's fine because these units are going to cancel anyway. Oops. So you have 0.75 molar. You have 2 here. And then that. Okay? So watch what happens. I want you to get comfortable with this. 0.75 divided by 2. That's your 37%. See? He's right here. 37.5. Okay? You're going to take 37.5% of this, 50 here. So you multiply by 50. So you only need 18.8 mLs of concentrated. That's what's going on here. You need 18.75 mLs of the concentrated. What do? You now take 18.75. Here's your graduate, right? You measure it up, 18.75 like that. You do. There it is, pretty. And you dissolve it in a beaker like that, a little beaker. And probably we should be more accurate, but we're fine. And then you add water until it gets up to 50 mLs, right? So then you add water. To 50 mLs. up to 50 mLs, right? So do you see that you don't have 50 mLs of water? You have 50 minus 18.75, okay? But that's how you do it. So then you would have, when you're done, this should be 0.75 molar HCl. You've diluted it, okay? That's very important stuff to know. We should do another one. That way you're comfortable doing this on your own. All right, so Benway has to make a batch of, let's see, if we have nitric acid, that's some pretty dangerous stuff. I think nitric acid comes as 15 molar. Fine. All right, so HNO3, when I get it in the bottle, is like 15 molar. That is extremely concentrated. Just the fumes coming off of that are bad news. All right? So we have this is 15 moles of HNO3 for every liter. Hugely concentrated. Very dangerous stuff. All right, so we need to do a lab where we only need, let's say, 0.300 molar for you guys. Okay? Much safer. Okay? But because I'm dealing with an entire class, I'm going to say that I need 800 mLs. That's the problem. I need to, and this is definitely stuff you're going to use in college. You need 800 mLs of this stuff, and they give you this dangerous looking, scary bottle. Here's this big old, right? This nice, dangerous looking bottle, skull and crossbones on the side, and it should. All right, so here's this really bad HNO3. Okay. Now, they won't make you do it, but they're going to, well, they might, not with the big bottle, but here's this idea. I get this stuff, like $40 a bottle or something like that. So what do I have to do? Start with what you know. We're trying to figure out, right? Concentrate, dilute. How much of the concentrate do you need? That's what we're doing here, folks. You need to know how much of that dangerous stuff do I need. So what do? The concentrate, MdVd, but remember I want you to do it this way. Okay? That's how you're going to see it in college. That's how you're going to see it in AP Chem. But look at this now. Let's do this first. The dilute concentration is 0.3 versus 15. Right? 3 out of 15 is 0.3, and then we come up with this 0.03 again. It must be our favorite number today. Okay? So it's going to be 3.3% of the 800. And you can leave these as milliliters because those other units are going to cancel out. So what do we get here? We get 0.3 divided by 15. Clear that? 0.3 divided by 15. Oops, I'm sorry, it is 0.02. Yep, I had another number. I had 5. Okay, sorry. 0.02, 20% times the 800. You only need 16 mLs of this stuff, right? So what does that mean? The concentrate. You need 16 mLs of the bad stuff. And then what do? You take the 16 mLs, measured carefully, of course, small. There's your 16 mLs. Pour it into a beaker or whatever. You know 800 is here. You can have this stuff in there first. And actually, it's not quite like that. We'll show you how to do it properly, but you should add the water. Let's do it this way. You should have the water in there first. Then you add this. That's first. This is second. And then you top it off with more water till you get to 800. Okay? And voila. You have magical 0.30 molar nitric acid. Still strong, not as dangerous. Okay? All right, let's do another one because this, like I said, is very important chemistry. All right, so how much dilute can we make? How much dilute can we make? All right. If we said, well, we have 38.1 mLs of, let's see, what do we got here? We'll just go back to acetic acid. We could go to that, acetic acid. 17.9 molar acetic. Very strong stuff. Okay. And we need, let's just say we need 1 molar. Okay. How much can we make? Bad grammar, but I'm not worried about it. Okay, so here's the idea. Let's do it again. There you go. We're trying to find out what is the volume of the diluted stuff, right? So let's keep this here. Not everybody wants to do the math by skipping steps. So let's leave this here. MCVC, that dilute, right? That's going to come over here now. It's going to look the same, but if you are careful, you'll see that it's not quite the same situation. So those should be like that. Get used to doing that, okay? So what's your concentrated here? We now have the 17.9 molar on the top. The dilute is 1 molar. That makes our math maybe easier. And our concentrated solution was 38.1 mLs. So now it's not a fraction, now it's a multiple. So 17.9 times 38.1. We can make almost 682 mLs. See it? Good. We're going to call it that and be done. 682 mLs of diluted can be made. Right? So we're not going to talk about too much more of this because you have the general concepts. Let's go back and make sure that we have all of the big ideas. Right? All right, so for concentration calculations, it's going to be important in acid-base chem and other places that you know how to do molarity, moles per liter. And this is a common way of talking about it by using brackets. Okay? Capital M is a representative of that. All right? One of the calculations is, what if you took a solid and dissolved it to a certain volume? You need to be able to get to moles first. That's the first step. Get to moles. This is going to be a separate step. Now, some teachers don't do it that way. I think you should. Moles first, then divide. Moles per liter, right? If you pay attention to units, this is going to go quick. Get comfortable using scientific notation because that is coming. All right? So this would be the concentration if you dissolved 2 grams. That would be the molarity. All right? Well, what if we have another situation where we know the concentration here, but we want to take out a small sample? Right? We don't always want to use 1 liter because it's expensive, or we don't need that much. Right? So what if we only needed 400 mLs? What if we only needed a small sample here? This calculation now shows you, first, get rid of liters, so you deal with moles. Right? Do you see? Follow those units, man. Moles here, then convert moles to grams. Right? And so now you would take this and you would realize that your sample, you have 38.7 grams in there. Another example here, if you take a smaller portion, the 21.6, you'd have only 2 grams inside there. Okay? Sometimes that's important. I need to get the liquid out so I know how many grams of powder are dissolved in there. All right? But also as common is this dilution formula, but it shows up in a couple different ways. This is the most common version. This is more specific, certainly helpful, right? You could write like this. This is a less common version, but you will see it. Same thing, just looks different, right? And the idea is that if I have concentrated HCl here, right? What if I needed to make that stuff? And so, or what if I had to dilute it, right? So the teacher gives you 2 molar HCl and you said, well, we need weaker stuff. So this is the math. Get comfortable with doing this situation here by putting them in parentheses first, because that ratio is going to mean everything later on in chemistry. Okay? This is specifically how you should do it, is you should put a little bit of water in there first, right? When you add chemicals, dissolve your chemical and then go up to the top line here. Okay, that's really how we should do it, especially with acids. We have to be careful. All right, and then this example here. This is very concentrated nitric acid. We have to be really careful with that. So 15 molars, too dangerous for lab. And if we only needed 0.3 molar, how would we do that math? So turns out we would only need 16 mLs. This is about maybe 4 or 5, about a quarter cup, let's say. And then here's how you dissolve it. Finally, if you wanted to make a big batch yourself, right? And we knew how much concentrated stuff we have, you could also do that kind of math. So all of this is going to be relevant stuff for future acid-base chem, especially when we get into pH calculations.